Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of financial data, bankruptcy data from the Taiwan Economic Journal from the years 1999 to 2009. And it's a bunch of different economic features, financial features. And at the beginning, as you saw, we have a bankrupt class label. We're going to try to predict whether a given client is bankrupt or not based on a bunch of financial metrics. So let's hop into the notebook. We are going to use dimensionality reduction today to try to reduce the number of columns in our dataset while still maintaining a high accuracy. So we're going to use NumPy and Pandas for working with the data. For visualization, we'll be using Plotly Express. And for pre-processing, we're just going to use the train test split function and standard scaler from sklearn. And then we're going to use all these different models. So we have logistic regression, k-nearest neighbors, decision tree, 2 support vector machines, one with a linear kernel, one with a nonlinear kernel, and then a neural network and 2 ensemble methods, the random forest classifier and gradient boosting classifier. Then we're going to reduce the dimensionality of the data using principal component analysis. So let's go ahead and import all of that, and I'll load in the data using pandas.readcsv. And we can grab the file path right up here, paste it in, and take a look. And so if you noticed, the data has already been scaled. It has actually been min-max scaled. So if we do data.describe, you can see that the mins are all 0, the maxes are all 1. And I can't see all the columns. I would like to see them, so I'm going to go up here and just type pandas.set option max columns none. And now I should be able to see all of them. Yeah, so we have a good number. I think 96 columns. So we have 95 features if you don't count the class column. And the thing is, we're still going to have to scale the data, because if we're using principal component analysis, one of the requirements is that the data is centered at 0 before we perform the transformation. So we're going to do a standard scaling instead of a min-max scaling to achieve that. And that will give each column a mean of 0 and a variance of 1. Okay, so these actually have been encoded already for us. The pre-processing has already been done on the dataset. We can get data.info. You can see that the non-nulls are the maximum number for every column, so we have no missing values. We also don't have any object columns we have to deal with. Everything is numeric already. So the only thing I'd like to check is, do we have any single value columns? So we can take a dictionary that's going to map the column name to the length of unique values in that column. So we take data subcolumn.unique and then take the length to count how many we have for every column in data.columns. And I'm just looking for if we ever have a 1 here, because that would mean we can drop that. We could also, oh look, we actually do have 1. Yeah, there it is. So, yeah, okay. So we probably want to drop this, because this isn't contributing anything to our predictions that we would make. There's no way to draw differences. I think this is it here. So these are all 1s. There's no way to draw differences between training examples using this column. So we're going to drop that column. Alright, so let's start pre-processing. Yeah, so I'm going to create a function called pre-process inputs. Let me just close this up. This function is going to take in a data frame. It's just going to make a copy of the data frame, and then it will return the data frame. But first we will drop that column. So df equals df.drop. That's the name of the column, and axis 1 for the column axis. So drop single value column. Alright, let's get the process version back in X. So we'll call preprocess inputs on our data, store it in X, and this should just be the same as data but without that one column. So we have 95 now. Okay, so we don't have to do any real pre-processing here. We're just going to split and scale the data. So first, let's split the data frame into X and Y. Y is going to be what we're trying to predict. In this case, it's the bankrupt column. So data df sub bankrupt. And then X is all the rest of the data that we're going to use to try to make the predictions. So we'll drop bankrupt and store the rest in X. Then we'll do our train test split. So I want to dedicate 70% of the data set to the train set and the other 30% to the test set. So we're going to use the train test split function from sklearn that takes in X and Y, and we'll split them the same way given a train size of 70%. It will also shuffle the data by default, so I'm keeping that on, and it will include a random state to ensure that the shuffle and therefore the split is always made in the same way. And that will return 4 new sets of the data, like this. The train and test set for our X, the train and test set for our Y, and then we'll scale. So I'm only scaling X. I want to keep the labels intact, so I want to keep these values intact. So we're not scaling those, but I also want to only fit the scalar to the train set, because we sort of want to pretend we don't have access to the test set when we're doing the scaling and pre-processing. So I'm doing scalar.fit on just the train set, xtrain, and then we're going to transform both xtrain and xtest using the fit we have just to the train set. So we can do that with scalar.transform, pass in the data we want to transform. Only thing is this will return a numpy array. So if I were to return this right now as xtrain, you can see it returns as a numpy array, so I can't really visualize it nicely. So what I'm going to do is turn it back into a data frame afterwards. But I want to include the indices and columns to be the same as they were. So index equals xtrain.index, columns equals xtrain.columns. Alright, now I want to do the same thing for xtest, so all I'm going to do is go in here and change these to xtest. Alright, and now I can return these 4 sets of data right here, get them back over here, and take a look. So xtrain is back in the data frame format, and the only thing that's been done is it's been scaled, and you can see it's been split into, this is just 70% of the original data, and does not have the Y, which is stored here in ytrain. This is just the class labels. And you can also see by the indices that the data has been shuffled. Okay, so let's start training without dimensionality reduction. I'll just say original data. So I'm going to create a dictionary of models. I'll actually call it original models. And this is going to map the name of the model to the actual instance of the model. And for the sake of time, I'll just copy and paste this in. I did it before. We have the name of each model paired up with the actual instance that we can fit to the data. So what we'll do is for every name and model in original models dot items. So dot items will return the key value pairs as tuples, which we can then iterate through 2 at a time like so. And then for each one I'm going to fit it on the train set. And I'll print out a little confirmation message that just says it was trained. Alright, there we go, they're training. And now I'm going to get the results. So what I'm going to do is create an empty list called original results, because we're using the original model. And for each model I want to return an accuracy score that was returned by the model.score function. So for every name and model in models.items, the result will be model.score, and we evaluate on the test set, and that will give us an accuracy value as long as it's a classification model, and these all are. So result will be our accuracy value. We're going to append result to original results. So original results dot append result. So we'll just store it in there, and then we will print out the name of the model followed by the accuracy value. So I'm going to display it to 2 decimal places with a % sign and format that with result times 100 since we're showing it as a percentage. Oh, this should be original models, sorry. Alright, and so these are fairly good. However, we have to note that we are dealing with a large class imbalance here. If we look at yTrain, well, yTest just makes more sense, dot value counts, we can see the class distribution, and you can see there's hardly any bankrupt examples. Pretty much all non-bankrupt. So we take the mean. No, that won't do. What I should do is divide this by the total, by the length of yTest. And you can see we have 96.5% of the data as 0. So this, you see most of these models are actually not even doing better than just simply guessing 0 for every example. A few of these do a little better. I think this one. Yeah, this is the only one actually. The only one that beats out just guessing 0. So I'm not really doing a model optimization video, so I'm not going to go into dealing with the class imbalance right now. I really just want to show you how dimensionality reduction can be used to generate similar results. So I could also do a confusion matrix, figure out what's going on, but I'm not going to for this video. So let's do the dimensionality reduction. So this is a form of unsupervised learning. We're using principal component analysis, or PCA. And basically the way it works is you take the data. Let's look at it. Well, I'll look at xtrain actually. So xtrain is currently, you can consider this as a matrix representing vectors where each column is a vector in 94-dimensional space. So you can sort of consider each column as a different axis, perpendicular to all the others in 94-dimensional space. So for a given example, for a given row, this could be the x-coordinate of that row, the y-coordinate of that row, the z-coordinate of that row, or rather, instead of row, example, training point. And then after the x, y, and z, these are all the coordinates along axes which we can't visualize because you can't really see past 3 dimensions. So you can consider up to 94 dimensions, even though you can't visualize it. So each one of these rows is sort of a vector pointing to along different axes. So each one of these is a perpendicular axis. Now, the only thing about this, if we look at the standard deviations of this, because it's been scaled especially, the variance in the data is all spread across the different features, across the different axes. But when we consider the data set as a whole, you can sort of imagine the data having some structure in this 94-dimensional space. And there might be a better way to represent the data in terms of variance. There might be some axis that is not one of these perpendicular axes, some combination of the axes that captures the most variance across the data. And so that's what principal component analysis does. It's a way to calculate that axis that across which the data varies the most. And you can actually do this for 94 different axes, again all perpendicular to each other, but this time shifted so that the axes line up with the greatest variance in the data. So the reason that's useful is because then we can drop the low variance features, which aren't really carrying much information, while still maintaining a large amount of the original information in the data. In this case, we can't really drop any of these because we're not sure exactly which ones are useful, and they all have the same variance. But when we do the principal component analysis, we can sort of be sure which of the new features we've generated have more information than the others. Alright, so let's do this. We're going to create a principal component object, PCA object, using the PCA class from sklearn. And in here we want to specify the number of components we want to generate. So essentially, the way this works is it'll originally calculate all of them. So let's say we keep the number of components to be the maximum number of columns, 94. And then we'll fit the PCA object, so let me set n components equals n components. And we'll fit the PCA object just to the train set, similar to how we did with the scalar. And I'm going to generate two new sets of the data once the fit has been completed. It will be xtrain reduced and xtest reduced, which is just the reduced form of xtrain and xtest. And for this, we'll use pca.transform on xtrain. This also returns a NumPy array like the scalar did, so I'm turning it back into a data frame. And I want to keep the indices the same. And the columns here are not going to be the same. The columns are going to be labeled PC1, PC2, PC3, principal component 1, principal component 2. So let's call that PC plus string of I for I in range 1 until n components plus 1. Alright, and we'll do the same thing for xtest. Oh, there we go. This will just be xtest reduced. So let's go and change these all to xtest. Alright. Alright, let's see this. So, oh, I forgot the parenthesis. Okay, so xtrain reduced. Alright, so this still has 94 columns. I set the number of components to 94. But you can consider this as sort of that shift I was talking about. Not actually transforming the data relative to itself, just sort of changing the perspective that we're looking at the data set on. So that instead of seeing the variance spread across all the different features, we're sort of ordering the features in terms of their variance within the data. So if we look at xtrain reduced dot describe, you can see the standard deviations start high and then decrease as we go. So the way this is calculated actually generates it so that the PC1 actually is the axis with most variance, PC2 is the axis with second most variance, PC3 is the axis with third most variance, and so on. So it's already ordered in terms of greatest variance. So if we wanted to plot this, I'm going to use plotly express to show this. So I'll create a new figure with px.bar. The x values will be the principal component labels. I'm going to do a horizontal bar plot. So we're doing, I'll just grab it from here, this column names here, which will just generate this on the x-axis. Then on the y, we're going to use a field or attribute from the PCA object that we fit. You can actually take explained variance, which will show the variance in each column in order. We can actually do explained variance ratio as well to get a percentage of the variance, or a ratio of the variance, or a proportion of the variance in the data for each principal component. So we're going to use this on the y. And then I'll just give it some labels. So we'll set the x to be principal component. The y will be variance ratio. and I'll give it a color. Oh, we'll color it on these y values, and we'll give it a color scale. So color continuous scale, and so we can set the low value and the high value in tuples. So the low value on the scale we'll do light blue, and the high value will do dark blue. And I'll give it a title. So proportion of variance in principal components. Alright, so we'll do fig.show and take a look. So here it is. You can see all the principal components, and as we go on, the variance is monotonically decreasing. So they have been ranked in terms of variance. Now, this is what I'm saying. You can see that these values here, these columns here, contain very little information. They contain very little variance. There's not much room for the data to move around there. So the way we can use dimensionality reduction here is to just drop off these lower columns, because they're not as useful to us as the higher columns. If we just take, for example, we could reduce it down to maybe 10. Just take these ones. We may lose some information here, but most of the information is being captured in the first few PCs. So we don't necessarily need all this. And we are only working with 100 features, so this isn't really something we have to do. But if you're working with a data set with thousands or tens of thousands of features, then finding a way to reduce the dimensionality while keeping most of the information in the data set is a very useful method. So let's try that. We'll just drop this down to maybe 10. And there we go. So these are our new features. We just removed all the lower variance features. Now I don't know, maybe we dropped too many, but we can take a look at how this goes. So now we're going to train on the reduced data. So I'm going to create some reduced models, which is just going to be the same sort of dictionary as before. So let me just copy this in. So the same models we're using, but this time we'll do for name and model in reduced models.items. And let me just copy this as well here. We'll fit the model and train it. And then we'll do the same thing as we did before for the results. Only difference is this will be reduced results, and we change this to reduced models. Alright, so this hasn't quite finished training yet. Oh wait, actually, I forgot to change this. This should be xtrain reduced that we're training on. And once we train on the reduced data, then we can evaluate on the reduced data with xtest reduced. Okay, and now, alright, so it looks fairly similar, but let's actually plot the change in performance between the reduced data and the new data. Alright, so we'll create a new pyplot figure, which will not pyplot, sorry, plotly figure, plotly express figure, which will be a bar plot. We'll also do a horizontal bar plot like we did before. This time, actually I didn't do horizontal before, sorry, this is a vertical bar plot. We'll do a horizontal one here. So the x is going to be the numeric range value, and to get the x, what I'm going to do is take the results, the reduced results, and find the difference between the reduced results and the original results, so we can see if there is a positive or negative change. Right, so what we'll do is take the original results. We'll use numpy.subtract to subtract two lists. We take the original results. Actually, I'll do reduced results first. and then subtract the original results. And that will return our floats that we'll use on the x-axis. Then our y is just going to be the names of each model, so models.keys. And we want to orient this horizontally. We'll give it some labels. On the x, we'll have change in performance. On the y, we'll have model. The color is going to be given by these x values. And we'll have a color continuous scale. Again, this time I'll have red for 0 and blue for 1. And we'll give it a title. Change in model performance after dimensionality reduction. Fig.show. What did we not append? Oh no, I appended to original results. Okay, let's do this one more time. I'm appending back to original results, and then down here I'm going to make sure I append to reduced results instead. Okay, now let's try this. Oh, this should be, I guess we can do original models, it doesn't matter. Oh, I misspelled this? Okay. Alright, here we go. So this is a bit surprising. If we look at the change, so let me get the original, where is it? Original values. So these are our original results here. And we'll just display them next to the reduced results. So you can see we actually have a negative performance for decision tree. It's pretty substantial. We have a 94% on the reduced, and we originally had a 95%. So it did go down quite a bit, but we actually have some models that have increased in performance when doing after principal component analysis. And these tend to be the more complex models. Not in all cases. We have a support vector machine with a linear kernel that also increased. So I can't really say why this happened. But you can see what we did lose, if we did lose, was not much. We did lose for the logistic regression model and decision tree, along with the random forest classifier. But what we sacrificed in terms of accuracy, we gained in terms of memory used. We're using much less memory to store the data set if we're using these reduced data. It only has 10 columns here. So yeah, so that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.